Hello, this is Dr. Embody, Department of Computer Science and Engineering, with a little bit of information about computing that's useful for lawyers. So what is a computer? Well, basically computers are all around us, right? I mean, our cell phone is a computer, the iPod's a computer, our car has dozens of computers in it, our printer is really a computer, etc. They're all around us. So then what is a computer? Well, here's a nice little diagram of a computer, and its basic components have some kind of input, some information coming into it, some control. Here we got this guy with a megaphone yelling out instructions to do things to the data that we have, and then on the way out we get some output. Two main components of our computer are the processor, which does stuff, and the memory, which holds the data that we're going to be operating on. And here's another picture, kind of the same kind of idea of what a computer is. There are the processors I've already mentioned. That's kind of the brains of it. That's where you do the operations, add, subtract, multiply, divide, etc. RAM, which is short for random access memory. That's where you hold the information that the processor is going to work on. Now, one of the things about RAM is that it's what's known as non-volatile, which means when you pull the plug, everything it remembers is gone. And that's why we have things like a hard drive on a computer that's non-volatile. Usually it's metallic, something like that. And on your smartphones, you'll have some memory that is also non-volatile. It's basically the same kind of stuff that's in your thumb drive. But that's the basic idea. We start a program, it's on our disk, the data gets moved into RAM, and then the processor can work on that data. Data goes into the processor, stuff happens, comes back out to RAM. And if we want anything that we want remembered after we turn the computer off, has to be moved back onto some kind of non-volatile information, such as our disk. And this little model of a computer ends up being important for for lawyers, because things like, hey, if it's in RAM, then when the plug's pulled, it's gone. And so if you're looking for it, it's not going to be there. All right, so what about data? Well, probably the most important thing about data is that everything is just a bunch of ones and zeros on a computer. And that's a critical thing to remember. That's one of the big things to remember out of this little talk today. Everything on the computer is a bunch of ones and zeros. Your documents, every letter, every character gets represented as some ones and zeros. It's like saying, A is 64, B is the number 65, C is the number 66, and so on. Pictures, it's a bunch of dots, known as pixels, and we have colors assigned to it, and the colors are numbers. So white might be 0, and then you might have 256 different shades, and so on. But effectively, it's a bunch of numbers that represent the colors and the intensity of the colors, and so on. Similarly with music, what is music? Well, music is a sound, it's a waveform, and all we do is keep track of how high the wave point is at various points in times. That's the sampling, and those heights are numbers, so the music is just a bunch of numbers. And similar way is movies. It's a bunch of pictures with associated sound. So everything is a bunch of ones and zeros. And how do they differ? And they really differ in how the zeros and ones are interpreted. So, we say, oh, let's look at this document. It's a bunch of ones and zeros. Let's look at them as letters. It's a picture. Okay, we'll look at the ones and zeros as colors. So it's all in how they're interpreted. And that's why you see files that have different extensions, a doc file for a Word document, JPEGs, MP3s, and so on. That tells the computer, hey, these particular ones and zeros, I want you to interpret them as music or a picture or whatever. That again becomes important to you guys if you're looking for forensic evidence Everything in the computer is a bunch of ones and zeros. It's all in how they're interpreted. All right? And in fact, even nothing is a bunch of ones and zeros. So there's no such thing as the concept of nothing in terms of computer storage. There always has to be either a 1 or a 0. It might be garbage, but there's never nothing. All right, so let's talk a little bit more about storage. Again, it's just a bunch of ones and zeros. I've already mentioned random access memory is volatile. That means it needs power. It actually has to be refreshed. And cold can actually slow volatility. So there are tricks that can be played if you want to grab information that's in RAM. If you can do it in a chilly place, it can take many minutes for RAM to lose its memory. So it's actually possible to yank memory cards in a cold environment and plug them in someplace else and hang on to most of the data. You probably lose a little bit, but not that much. So cold could be a factor there. The hard drive, the disk, that's non-volatile. It's usually magnetic or optical disks like CDs and DVDs and things like that. And then more recently we have these solid-state disks, SSDs, sometimes called, more properly called solid-state drives. And those are really, it's the same stuff that's in your thumb drive, and it's just a way of storing data in a non-volatile fashion. And so this technology that we see in thumb drives, that's what's in SSDs, and it's also in the memory, say, that's in your smartphone. How about deletion? Well, deletion on a computer really doesn't delete. Because remember, there's no such thing as nothing. A reasonable analogy is that suppose we're looking at a hard drive and we delete a file on the drive, then what we're really doing is just deleting the entry in the table of contents. The information is still there. The whole file is still there. We've deleted the entry in the table of contents, and so from a forensic standpoint, we can still go get the file if a new file hasn't overwritten it. I mean, at some point, we keep tossing files into the same parts of the disk or in memory, and when we run out of space, we'll start overwriting stuff. And so the more full a disk is, the chances of overwriting are greater. Same types of thing happens when you compact a disk, right? It moves the files around, and in that way, files that had been quote unquote deleted will now in fact be written over. But the important thing is that when you do delete, just changes the table of contents, and the information is still there unless there's something else that happens that maybe overwrites it. How do I actually really delete stuff? If I want to ensure that it's gone away, then you just overwrite it with either just random ones and zeros, or just like all ones or all zeros, or something along those lines. And so now, if you're a criminal and you want to protect your data, you can write a program that, if you don't enter your password every day, the computer will just go and randomly write ones and zeros all over your disk. There's various myths about how often you have to do that. There's DoD specification that says you got to write it a dozen times or whatever. That's been actually proven to be unnecessary. One set of writes will make it effectively unavailable. And of course, there's destroying the disk. It's magnetic if it's a hard drive, or you can beat it with a sledgehammer. There's various things that can be done, and those are very effective ways to delete stuff. Nice example of forgetting to do this: in the 2008 post-election, the McCain campaign, after losing the election, they auctioned off all the stuff that they had, and in particular, nobody deleted the information from the BlackBerries. They sold those BlackBerries, had all the phone numbers, emails, all that kind of stuff on them. So, deletion can actually be an important thing, and major people can forget about that. So disk forensic then ends up being about mining these so-called empty parts of the hard drives. There's information that's out there, whole files, the table of contents have been deleted, but the stuff is still there. And disk forensics is about going out and finding that stuff. And so when you image a drive, you're just grabbing, it's a snapshot of all the ones and zeros out there, and there's lots of tools that they charge a lot of money for in many cases that will help you figure out what these ones and zeros mean. So there's a bunch of ones and zeros out there. There's no file name associated with it, so there's no file extension. So what, is this an MP3? Is it a doc document? And there's, there's software out there that helps you figure that out. And you don't need to do that. There are people that get hired to do that, but that's basically what they do. A little twist here. I mentioned the solid state drives, which, like as I said before, is pretty much a big thumb drive. Deletion is a little bit different, and the courts are going to have to work through this because what happens is a write really is a read erase write of the block, which is hundreds of bits. And there's actually routines that get called garbage collection that go around in the background that will actually do this pre-erasing of the information. So I'd mentioned before there is no such thing as nothing there, but there sort of is with the SSDs, and effectively it doesn't matter that much, except now when we take an image of a disk. If that drive is still attached and powered up, then there's stuff going on in the background that's preparing for the deleted areas for use later on. And so so we'll have this concept now of imaging an SSD drive at two different points in time, and in fact they will differ slightly. We didn't have that problem with a hard drive. A hard drive is sitting there plugged in, and as long as nobody's writing anything new to it, it doesn't change. SSDs are a little bit different. It's going to be a while for for people to figure out in a legal sense how we're going to handle that. Because this imaging analogy is a little bit different. Is it enough to make a difference? I think time will tell. Okay, shift gears. Encryption. Let's take a look at encryption and why you care about encryption. Nice little cartoon to give you an idea about it. This is from XKCD. If you have a little trouble reading it, I give the URL down on the right-hand corner, xkcd.com/538. So here's the crypto nerd's imagination. His laptop's encrypted. Let's build $1 million cluster of computers to crack it. Oh no, good, it's 4096-bit RSA. Oh no, our evil plan is foiled. Reality, what would happen is, hey, his laptop's encrypted. Drug him, hit him with his $5 wrench until he tells us the password. Got it. And that's actually pretty close to reality. Are you going to crack an encrypted disk? The answer is no. What's the best way to do it? Get the password. If you can't beat it out of them, maybe you can guess it. So really what's happening here is this notion of hiding data in plain sight. If the data is important, it's got to be encrypted. If it's not encrypted, there's two interesting things. Let me back up. There are, I think from a legal, from a lawyer's standpoint, there's two things that you're interested in here. One is, what about your data? Your data ought to be encrypted. If it's important, it ought to be encrypted because somebody can get into your computer and now they've got your data. On the other side, suppose that you're trying to get somebody else's data. Well, if it's encrypted, you can't get it. Sorry, game's over. And if it's not encrypted, okay, maybe there are ways to get it. So from that, so what is encryption? Well, really what encryption does is it randomizes data. It basically, so what should be an organized set of ones and zeros that are representing characters or colors for a picture or whatever, now are effectively randomized. and that's what encryption does. And then the important part now is it possible to now extract out the data that you want. It just as an aside, only use public open state-of-the-art If somebody says they've made up some kind of their own encryption thing, run. Don't walk away from that. Run. They don't know what they're talking about. The thing that's important here is that for all intents and purposes, if somebody has encrypted data, it is impossible to extract. Now there's a key or a password to to decrypt that file, and now it's a task of, can you guess that key or password, or can you find it hidden someplace? But short of that, you're not going to decrypt it if it is using a open state-of-the-art encryption method, which are free. So chances are, if they're at all smart, they've done it that way. So, like I said, it's all about the key at that point. And you guess it, you beat it out of somebody, whatever. Just as an aside, there's an interesting thing called steganography, where you hide data in a picture. So, what this means is that if you've got 256 colors for each pixel in a picture, well, if you changed one of those bits from a 1 to a 0, hey, now you have stored one bit of information in each pixel of the picture, and so you've got this picture whose color shades have changed by an insignificant and unrecognizable amount, but there's actually data hidden in there. It's kind of an interesting way to pass data around. It gets hard to realize that you have an encrypted piece of information there, and it's difficult to get out. So, impact for you. You've got search warrant for data. If the data is encrypted on the disk or the hard drive, it may be accessible while the computer is on when it's in the RAM, because at some point the criminal is viewing this data, or the person that whose data you're after. The information is in RAM while it's being processed by the computer. It's actually decrypted at that point. So if somehow you can grab it while the computer is on and the information is in RAM, then you still have access to it, even though it's encrypted on the disk. Shut the computer off, boom, it's gone. Yeah, it's now totally encrypted, you can't get it. The other thing is that sometimes the key itself will be in RAM while the computer is on. And then if you get the key, well, then who cares if you turn it off, because you've got the key and so on. The tools exist to keep computers on while they're being moved. So a computer's plugged in someplace. There are tools so that you can actually transfer it to a battery without ever turning it off. It's kind of some neat little technology, but that kind of thing is possible, and then you can keep the computer on, and now you can look at all the information that's in RAM. We end up with an interesting problem from a forensic standpoint. Is unlike a disk, RAM is volatile, it's changing all the time. It's a lot harder to establish that it hasn't been changed. Okay, another impact for you. Sharing of your own data. Well, if it's important, it ought to be encrypted. So you've got different law firms working on some information. Pass it from one place to another. It ought to be encrypted. Stuff happens. If you've encrypted it, now you've reduced the problem to sharing the keys. That is the password. You can send an encrypted disk through regular mail or FedEx or whatever, and over the phone, tell them what the key is. A couple of document gotchas for you. Microsoft Word keeps changes in the documents, and they can be easily recovered, and so you should be aware of that. Don't share Word documents with somebody if you don't want them to see the changes that you have. Yes, there's ways to turn it off, but it's better to just not share them. PDFs, some people will black out data by adding a layer of black rectangles on it. Guess what? That's a layer of black rectangles on top of the document, and you can just remove the layer, and now you can see everything underneath. But PDFs are, if you're not trying to redact parts of information, PDFs are great ways to share data. So you take a Word document, you convert it into a PDF, and then share that with somebody else. Your changes won't be in there because you've changed the medium that you're doing. How about integrity of data? Well, as an example, Professor Corbett has nude pictures on his computer. How'd they get there? Well, integrity of data is interesting. Integrity is binary. It's either you have integrity or you don't. There's no middle ground. It's sort of like you can't be sort of pregnant. You're pregnant or you're not. There isn't a middle ground there. It's difficult to guarantee the integrity of data. Tools exist to track changes and notify you when changes occur, but they're not commonly used. So how do you determine that there really is integrity of data? And it's important to people like banks, for example. But that's numeric, and there are numerical methods to doing this. I use the example of funny pictures on Professor Corbett's disk. Well, there exists code that when you visit a website can transfer data to your machine without you knowing. It's called a drive-by download. One way this can happen, there might be a legitimate site and there's a frame in the corner with an ad in it. Without you clicking on it, that ad takes you to a web page. That web page now, through your browser, moves data onto your computer, and you don't even know that it happened. So, guaranteeing that someone else didn't use a computer can be difficult to establish is another problem. So you've got a computer, Corbett's computer's got some funny pictures on it. How do you know that he was the one who put those on? It might have been a drive-by download that he was unaware of. It might have been somebody else with access to his computer. It's really hard to establish that. So tying an individual to data can be problematical. There's just many different ways that tie can be broken, and that can be if you're trying to defend somebody who has some funny stuff on their computer, there's a lot of possibilities. There's all sorts of ways that stuff can get on the computer without somebody else knowing about it, because we're in this connected world. Some other issues. How about the cloud? What do we care about the cloud from a legal standpoint? Well, you can keep your data on the cloud. Where is it? Who owns it? How can you get it? Who do you trust with your data? In particular, what happens when you have entrusted your data to some company and now they get sold? That data now has some value, and when when they're trying to determine the value of the assets, that data may have value and can be sold. And so now where is your data? And by the way, if it's encrypted, who cares? Then, if your stuff gets sold, if you've encrypted it, then they really don't have access to it. But there are things like the Google Apps, stuff's out there in the cloud. There is the thing called the Internet Archive. Well, that's kind of interesting because that's trying to keep snapshots of the web. So if you're looking for information on somebody, it might be in the Internet Archive. Google indexes the web, and they also cache stuff. So web pages that were there but now aren't might still be in a cache someplace. So the impact for you is the data you seek about somebody might be out in the cloud. Another place for data. How about backups? Well, there's really two sets of people. Again, and here's something for your personal use and for investigating other people. There's two kinds of people. People who've lost their data and now back up data, and everybody else. Back up your data. Back up your pictures, back up your stuff at work. If you're not backing it up, you're going to lose it at some point. And now imagine that your stuff is lost and it is impossible for you to get So that's one in terms of personal usage. But there's another side to it. Another impact of it is, where are the backups? And are there automatic backups that people don't know about? We have the Petraeus case in 2012. There was data about emails that was out in the cloud, and the people didn't realize that stuff was out there. So not only can you go looking for backups, but you can try and see if there are places where things were automatically backed up out into the internet someplace that maybe the people didn't even know about. It's out of their control. Can you get a hold of it? Metadata. Metadata is data about data. That can be really useful, right? Like the index of Google, address books, emails, cell phones, location by cell tower. Right? Where is a phone? Facebook friends. Right? That's information about people through other people. And give me 6 pieces of data about somebody, and I can identify the individual. In fact, often you can identify the individual with a lot fewer pieces of data. Give me someone's mother's maiden name, and I can steal their identity. So, data about data is really useful for finding people. It's also really useful for finding information about people's characteristics, movements, etc. So, again, 2 sides to it. Your own personal information is out there, and if you're looking for information about somebody else, there's information out there. So data about data can be as useful as the data itself, and data about data, that is the metadata, is often forgotten about people. Digital signatures. Okay, so this is under the personal use. What do you care about? It's signing a document. Why should you care? Well, it lets you authenticate a message. You can decide that this message was actually sent by the person who claims to have sent it. And it also keeps you from somebody forging your email. So there's a correspondence that you have, say, with another person, a firm, or whatever. Were you the one that sent it? And there's an integrity checker as part of this. Has somebody changed the email after you sent it? So it's like, hey, you sent me this email that said this. You go, no, I didn't. How do you establish that? Well, if you've used the digital signature, you can in fact establish that. Not only were you the one who sent it, but you can establish that whether the message has been changed since you sent it. Very, very useful in terms of personal usage. Now, on the other side, there is a piece of email. Who sent it? Has it ever been changed? Very, very difficult to establish that. How does digital signing work? Well, let's take a quick look at it. Well, what we're going to look at is taking an email and signing it. So here's my data, that's my email. I'll run it through what's known as a hash function, and I come up with a bunch of 1s and 0s of a fixed length. I will then take that hash, encrypt it using a key, and now I have a random looking set of 1s and 0s that incorporate 2 things. One is the data itself, and the other is an individual's key. Both of those combine together, and this signature now will represent who sent it and what exactly was sent. And I will attach that signature to my email, and now I have digitally signed email. If you may have occasionally seen an email, and down at the bottom there'll be something like PGP signature and a bunch of characters, a few lines of characters. That's the key at the bottom of the email, and it incorporates 2 things: who sent it and what in fact was sent. So on the receiver side, if I want to verify it, I will take the original email I'll run it through the hash function and come up with a hash value. That is doing exactly what was done at the beginning. If I take that email and I run it through the hash function, I come up with a hashed value. I can do this because this is a one-way function. So that in a one-way function, what it does, if I look at the hash, it tells me nothing about the data. Example of a one-way function, if I take 2 and I square it, I get 4. If I take -2 and square it, I also get 4. So if I look at the number 4, I have no way of knowing whether somebody started with a +2 or a -2 when they squared it. So a squared function is an example of a one-way function. Look at the 4, it doesn't tell me anything about what number was started with. And these hash functions have that characteristic. I look at the hash, doesn't tell me anything about the data. So I'm going to take the original email, go through the same hash function, and come up with a hash. Is that the same hash that the sender had? Well, to do that, I take the signature, decrypt it, and that should give me the same hash function. What I'm doing here is that is a reverse of this process. So it's the same going from the signature. Now, do I extract out the same hash? And then I just ask the question, are they the same? So if the signature is the same, that captured the original data and the user, is that the same as what I find when I simply run the hash function through it? And again, why do I do it with the hash function? I do that because the signature used the hash, and the hash is a fixed size compression of the information that's in there. And these hash functions have to have the important characteristic that if I have a hash, I can't figure out what the data is, and that there are not two pieces of data that will have the same hash. So that's the way, that's sort of a little bit of an idea of how the digital signature works. Maybe a little more than you wanted, but it lets you see how it is possible to sign a document and establish the integrity of the data and who sent it. So what gets used for it? Well, pretty good privacy. It's an open source, publicly available. It used what's known as public key cryptography. That's one of the things that we would use for signing an email. So you want to sign your emails? PGP is a good way to go. And, by the way, if somebody uses PGP to encrypt data on their hard drive, you're not going to decrypt it. The only thing you can do is go after their key. Well, we have to talk about passwords. How do you create a secure one? Should you write it down? Let's start with creating a secure one. Length is important. Length is important. Having multiple words, random sets of characters, etc. But length is really important there. And you ought to be getting past 8 characters if you want a secure password. Should you write it down? That's a good question. The answer is actually yes. Write down, get a complex password, write it down, and protect it. So most passwords, the amount of security that you need for it is about the same as security of things you carry around in your wallet. So create a complex password for important things, carry it around in your wallet. If you lose your wallet, guess what? You can make a new password. There's a nice little example, another XKCD. It's xkcd.com/936. Might be a little hard to read on this screen. Take a breather, open it up, xkcd.com/936. Nice little discussion of passwords. A rough idea of what's going on here is you can have a kind of a hard to remember password, not very long, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 characters. There are different ways of determining entropy in terms of how hard it is to do. Relatively easy for a computer to guess, really hard for you to remember. Here's 4 words in a row, nothing to indicate where one starts and where one's end. It actually has 44 bits of entropy. It's hard to guess. It's pretty easy to memorize it. If you can figure out a way to work in some uppercase and lowercase, that can help out. But don't do something like make the uppercases there, because then it becomes easier to figure out what it is. How about crime today? Well, you'd be interested in this one. What's the most lucrative online crime today? Well, stealing from the little guys, but not the real little guys. Stealing from medium-sized companies. How do you do it? Well, you steal the banking credentials. If the bad guy comes and steals steals the student's banking credentials, they may get a few $100. A faculty member's credentials, they may get $1,000. Not a big payoff. But you go after a small company, 50 employees. Now they may funnel hundreds of thousands, or even if there's a lot of inventory, millions of dollars can funnel through a small company in a month. So if you can steal their banking credentials, you can have access to a large amount of data. Most banking credentials are stolen through browsers. So one of the most important things to do is always to keep all your software updated. Operating systems should be on automatic updates. These days, keeping your browser updated is critical. It has to be done automatically, so that you grab all the latest ones. It's an interesting question of who's at fault when your banking credentials get stolen. So there's a very interesting case that was working through the courts recently, Patco versus Ocean Bank. And here we had Patco, family-owned business in Sanford, Maine. They sued Ocean Bank, their local bank, after discovering that hackers were siphoning about $100,000 per day from its online bank account. The hackers had sent a malicious email to employees that allowed them to surreptitiously install the Zeus password stealing Trojan on an employee's computer, actually also known as the Zeus botnet. And what the Zeus does is it steals stuff within the browser. So the Zeus software made it on to a browser that was doing the banking. They grabbed the accounts and password, and then they sat and waited until there was a lot in the bank. And then they started stealing. They actually stole, this went on for almost a week. They got about $600,000 before the company realized that it was going, that was disappearing, and they actually managed to, with the help of the bank, they stopped about half of it. So they had about $300,000 loss that was in this particular case. U.S. District Court in Maine said that the bank wasn't at fault. The problem was with the employees. The problem was with the company. It went up one more level. The First Circuit Court of Appeals then ruled in July 2012 that the bank security system wasn't commercially reasonable and advised the two parties to settle, which they did, and the bank, which basically what the end result was, the bank refunded the money, the company ate their lawyers' fees. So, but interesting thing, how, where is this particular case going to go? Who's at fault? In terms of, and there are some interesting things about this, like all of of a sudden, this bank which didn't move large amounts of money, all this money was being sent overseas. The bank had triggers to identify that, and they weren't acting on those triggers. So it's relatively narrow, but anyways, it's interesting. Who is at fault when something like this happens? Should the bank be making a better effort to do this? One thing you can count on is that there is no such thing as perfect security. So you cannot say that a family-owned business can't make mistakes. There is no way that anybody's going to get onto their computers. That's one thing you should remember. There's always a way to get onto a computer. It's just how much money, how much effort. Do you have it at hand to get in there? And that's that's the critical part. There's always a way in, and that's something that's an important takeaway from this. There is always a way onto a computer. Always, always, always. It's just, do you have enough money? Do you have enough time? Do you have enough skills to do it? And if you've got those three, there's always a way on. Okay, if you want to do a little bit of simple cryptography, take a piece of paper, write down the alphabet, choose a number between 1 and 24, let's call it K. Count along the alphabet K letters, and at that point start writing the alphabet again below the starting A, wrapping around at the end. Now you take some word you want to encrypt. You can encrypt the word, put it on a piece of paper, and pass it to a neighbor. See if they can figure out what it is. And so here would be an example of a cipher. We have, it starts this is the normal alphabet, A, B, C, D, and so on, and we've shifted it over 3. And so A, B, C, D, and then we wrap it around. When we get to W, we go back to X, Y, and Z. So how do you encrypt something here? Well, suppose I want to take the word cat. So I take C, which is the letter Z. I take the A, which is the letter X, and I take T, which is the letter Q. And I went wrong, hit the wrong button here. Let's go back. There it is. So C went to Z, A went to X, T goes to Q. So I started with cat, and I ended up with ZXQ. Turns out the Caesar, so this is a simple way to transform from one set of letters to another set of letters. It's called the Caesar cipher because Julius Caesar used this back in the Roman days. It is actually easy to crack this kind of cipher, usually using things like, okay, E is the most common letter in the alphabet, and look for the most common letter in your code, and that gives you an idea as to where, what this number K is. But it just gives you an example of how you can transform one into another. So, what are some rules about cryptography? Well, you should only use some kind of a public, well-known encryption algorithm so that only the key is secret. This should be about managing keys, not about managing the secret of the algorithm. The current standard from the National Institute of Science and Technology is AES. It is effectively unbreakable. So now your problem is really moved from securing the information to distributing the key. It's what's known as symmetric encryption. Both parties have to have the same key. If you're curious, there is an animation of it, of how it works. It's kind of fun to look at. It's this animation, and you can just see the lengths that the AES algorithm goes through to scramble up what it starts with. And that's what's, it's kind of fun to look at. How much effort has to go into scrambling it to make it secure. That's it. So, a few things that I would like you to take away. One is that all information is just ones and zeros. Deletion doesn't really delete. Encryption, stuff cannot be decrypted. And it's a good thing for you to use with your own information. Finally, last but not least, is that from a security standpoint, there's always a way to crack a system. So that's why you want to encrypt your data. Always assume that somebody's going to get a hold of your data. There's always a way to do it if they are highly motivated and have the skills to do it. Feel free to send me an email with any questions. If I get enough questions, maybe I'll make a video response to this. Have a good day. Bye.